Hi, in this video we'll be doing some more practice problems with buffers. So the first problem asks, what is the pK of, if the pKa for acetic acid is 4.74, what is the Kb? Now pKa is equal to the negative log of Ka. So 4.74 is equal to the negative log of x. So to do this, let's first change this into negative and turn this into positive, and take the antilog of both sides. So 10 to the negative 4.74 power is equal to x. Now 10 to the negative 4.74 power is going to give you 1.82 times 10 to the negative fifth, and that is Ka. Now to take the Kb, Kw divided by Ka is equal to Kb. So 1.0 times 10 to the negative 14th divided by 1.82 times 10 to the negative fifth will give you the Kb, which is 1.0 e to the negative 14th divided by 1.82 e to the negative fifth, which will give you 5.50 times 10 to the negative 10th power. Now the answer is 5.50 times 10 to the negative 10th power. And that is our Kb for the solution, for acetic ion. Now what is the pH of a 500 milliliter 0.12 solution of acetic acid? Well, acetic acid is HC2H3O2. And now we have plus H2O, which forms C2H3O2 minus plus H3O plus. Now over here, this is 0.12 molar as we're given. This is, we're not going to care about water. It's going to be 0, 0, and yes, that's it. All right, so this is going to be minus x. This will be 0.12 minus x. Be plus x, x, plus x, x. Now, what is Ka for acetic acid? Ka for acetic acid is 1.8 times 10 to the negative fifth power. So 1.8 times 10 to the negative fifth power is equal to x squared divided by 0.12. And see that x is so small, we can ignore this minus x. So 1.8 e to the negative fifth power times 0.12, and take the square root of that, we will end up with x is equal to 0.00147. Now this is the concentration of H2O plus, so negative log of x is equal to pH, which is equal to 2.83. Alright, the next one, we have the solution involved is mixed with 500 milliliters of a 0.02 molar aqueous potassium acetate, which is K acetate, will have C2H3O2, potassium acetate. Okay, now what is the pH? So potassium, K, is going to be a spectator ion because KOH is a strong base and K is the weak conjugate acid. So it's weak, we're going to cross it out. Now we're left with C2H3O2 minus. Alright, now we're adding our acetic ion, but we also have a solution with it. So we're not just dropping solid potassium acetate into it. We actually have an aqueous solution. So that means our solution will double, 500 ml plus 500 ml, which means our new concentration is going to be 1 molar. So in the previous problem, we have 500 ml for 0.12 molar of acetic acid. And now this will turn into the new solution of 1L times x molar. So 500 times 1.0, so it's going to be, this is going to be 1,000 because we're counting milliliters. 1,000 milliliters times x molar. So 500 times 0.12 divided by 1,000, basically 0.12 divided by 2, which is going to be 0.06 molar. This is going to be the concentration of HC2H3O2. And now our aqueous potassium acetate, we also have 500 milliliters, and this time it's only 0.02 molar is equal to 1,000 milliliters, our same solution, times x molar. So this is 0.02 divided by 2, which is going to be 0.01 molar of C2H3O2 minus. Now we're free to use the Rice chart again. HC2H3O2 plus H2O forms C2H3O2 minus plus H3O plus. This will be 0.06 over here. It's going to be 0.01 instead of 0. We're going to cross water out. It's going to start with 0. Minus x, plus x, plus x, 0.06 minus x. Let me write the rice over here real quick. And this is going to be 0.01 plus x, will be x. Our k did not change, which is still 1.8 times 10 to the negative 5th power. From above, it's the same acetic acid, so 1.8 times 10 to the negative 5th is equal to 0.01 times x divided by 0.06. Again, we remove these plus and minus x because it's so small. Now we 1.8 because the k is too small. 1.8 times 10 to the negative 5th times 0.06 divided by 0.1. That gives an x of 1.08 times 10 to the negative 4th power. Now take a negative log of x, which will give us a pH of 3.97. Now if you didn't want to use the Rice method and you wanted to use the HH equation, which in my opinion is easier. So from now on, instead of doing these Rice charts, we're going to be using the HH equation. Alright, next, if 0.025 moles of solid KOH is dissolved in the buffer valve, what is the new pH? Notice this time we did not have any new volume. So this time we can just simply add it into our RBCA chart, right? Include more stuff. RBCA. So the reaction is still going to be the same. H C2H3O2 plus OH plus, okay, this time we're adding KOH, sorry. This time it's no longer the same reaction, and this is why we need to use the Rebecca chart, because we're not using the common ion effect there anymore. We're not adding potassium acetate. This time we're adding a new different type of solution, which we need to use a RBCA chart to show the consumption of this OH minus. Now this will form C2H3O2 minus plus H2O. Since we're not dealing with this new solution, so we have to use all the numbers from our previous question. Now fortunately, we ended up with one liter, right? So all of these moles, so let's use 0.06 for this, 0.06, and 0.01 for C2H2O2. So it's going to be 0.01. Now OH minus, we have 0.025 moles. And it's also going to be 0.025. Notice all of these are in moles, right? Why are these in moles as well? Because in our previous solution, we have 1 liter. We have 500 milliliters and another 500 milliliters, which form 1 liter. And 1 liter, we can easily convert these molars back to moles. If this wasn't 1 liter, you have to divide these two by the liters of the solution to get moles, and then plug these numbers in. Since we have an easy 1 molar, these 0.06 molar and 0.01 molar will be easily converted to moles. Okay, now we have moles. We can do minus the smaller number, which is 0.025. Now 0.06 minus 0.025 is going to be 0.035. This is going to be 0, and this will be plus 0.025, and this will be 0.035. So now we'll convert both of these back to molar in order to do the HH equation. So this will be 0.035 molar, and this will be 0.035 molar. Now the HH equation, the pH is equal to pKa plus the log of conjugate base over acid. Now what is the concentration of conjugate base? 0.035. And again, our mole number and our molar is the same because we're in a 1 liter solution. So this is 0.035 molar and 0.035 molar. So when we plug this over here, and this over here, this is basically log of 1, right? And 10 to the 0th power is 1, so it will be log of, so this will be equal to 0. And when dealing with logs, when we are doing anything to the log of 1, it will be 0. So when 0, it can be crossed out. So pH is going to be equal to the pKa. And what is the pKa? pKa is going to be the negative log of K, which is 1.8 times 10 to the negative 5th. So negative log of 1.8 e to the negative 5th will be 4.74. So pH is going to be equal to 4.74. Next, we're going to add more KOH. So we're going to have to do a new RBCA chart. And this time, what do we have? We have HC2H3O2 plus OH minus. Again, K is not included because it's a spectator ion, which forms C2H3O2 minus plus H2O. Okay, this time these are molar, but we can convert it straight back to moles. So let's use everything from the previous problem because we're still in the same solution. This will be 0.035 moles of CH3O2, and this is going to be 0.035 moles of C2H3O2 minus. Our KOH is going to be 0.2. Alright, so what is the smaller number over here? Our smaller number is 0.035. So it will be minus 0.035. And now this will have no more H3O2, and we'll have 0.2 minus 0.035, which will be 0.165. This will be plus 0.035, and this will be 0.07. Okay, now what do we notice here? We have no more Hc2H3O2. So what happens when we try to use HH equation? We have pH is equal to pKa plus the log of conjugate base, which is 0.07, over acid. But we have no more acid left, so it'll be divided by 0, which will give us an error. So what do we do over here? Well, since we have this time we're left over with OH minus, we're going to use our concentration of OH minus to find our pH. So let's convert this 0.165 moles of OH minus back into molar. So we're going to have 0.165 moles of OH minus converted into 0.165 molar of OH minus. Now that is done, we can use pH is equal to the is equal to the 14 plus log of concentration of OH minus. So we can do 14 plus log of 0.165, and that gives us a pH of 13.22. And that is our new pH. So when we have excess OH, and if you're dealing with the opposite, you have excess H3O plus, you can just take the concentration of OH minus or H3O plus and take the negative log of that and add 14 if necessary to find yourself the new pH. Now we're here. What is the pH of a 1.00 liter solution of ammonium chloride? Ammonium chloride is NH4Cl. HCl is a strong acid, which means Cl minus is a weak conjugate base, so we're not going to include it. So NH4 plus, which is our original, let's add into water to find the pH, plus H2O, which will form NH3 plus H3O plus. Now this will be 0.24. Unfortunately, we're dealing with 1 liter again, so moles and molar can be easily converted. And to find pH, we're going to be using the Rice chart. So let's cross this out. This is going to be 0, 0, minus x, 0.24 minus x. This would be plus x, this would be plus x, this would be x over here and x over here. Now what is the Ka for NH4? Ka for NH4 is 5.6 times 10 to the negative 10th. So 5.6 times 10 to the negative 10th power is equal to x squared is equal to x squared divided by 0.2. Now we divide 0.24, sorry. Now we can remove this minus x because of how small our K is. Now we do 5.6 e to the negative 10th power times 0.24 and take the square root of that, which will give us an x of 1.16 times 10 to the negative 5th power. Now we can take the negative log of that to find the pH, and the pH is going to be 4.94. Next, if 0.12 moles of solid NaOH is dissolved, so NaOH is a strong base, so Na plus is going to be a weak conjugate acid, so Na will be a spectator ion. Now we'll only be adding OH. So let's see, our previous solution we have NH4 plus plus OH minus. We're adding NaOH to our solution of ammonium chloride, which forms NH3 plus H2O. Now this will be 0.24, and we have to do Rebecca chart because we're adding a new species. We have to show the consumption of these moles. So 0.24, 0.12. Again, we converted it from 0.24 molar to moles because we're in a 1 liter solution. Now this is gonna be 0 and 0. Actually, this won't be 0. This will be x, which is 1.16 times 10 to the negative fifth. But because it's so small, we can ignore it. Now this will be minus x, plus x, plus x. Oh wait, no, sorry, this is Rebecca chart. So when you do this, it's gonna be minus 0.12. This is gonna be 0, and this is gonna be 0.12. This is gonna be plus 0.12, and let's cross this out. It's gonna be 0.12. Right, now we have the RBCA chart. We convert it back to moles, which will be 0.12 moles and 0.12 moles. So we can use the HH equation. pH is equal to pKa plus log of conjugate base divided by acid. Conjugate base is 0.12. No, sorry. Conjugate base is 0.12, and acid is also 0.12. 0.12 divided by 0.12 is 1, and log of 1 is 0. So this is 0, and we can cross it out. Now the pH will be equal to pKa again. So what is the pKa of NH4? Well, we found the Ka, which is 5.6 times 10 to the negative 10. So we can take the negative log of that. Negative log of 5.6 e to the negative 10th, which will give us a pKa of 9.25, which will be equal to the pH. Alright, now I have the final question. This says, what is the pH of 0.2 molar solution of sodium bicarbonate? Sodium bicarbonate is going to be NaHCO3. That is our sodium bicarbonate. Na is a spectator ion, so that's going to be ignored. Now I have HCO3 minus. Let's see, we have two possible solutions, right? We can have HCO3 minus plus H2O, forming CO3 2 minus plus H3O plus. Or we have HCO3 minus plus H2O, and this one is it donating a proton. This one can also accept a proton, forming H2CO3 plus OH minus. So now let's compare the K and the KBs. This one is producing an H2O plus, so let's use the K for HCO3 minus, and this will be the Ka2. Ka2 for HCO3 minus is going to be 4.8 times 10 to the negative 11th. 4.8 times 10 to the negative 11th. And we use Ka2 because of what our product and reactants are. We have a CO3 2 minus and HCO3 minus, which means we can only use a Ka2. Now this one, since we're producing an OH minus, we're going to be using Kb. And what is our product and reactants? We have H2CO3 and HCO3 minus, which means we're going to have to use the Kb of Ka1. Ka1 is 4.3 times 10 to the negative 7th. So Ka is 4.3 times 10 to the negative 7th. Now we can take the negative log of that. No, we can take the 1.0 e to the negative 14th divided by 4.3 e to the negative 7th, which will give us a Kb of 2.33 times 10 to the negative 8th. Which one is bigger? This one is bigger. So this is the equation that we're using, and we can process out. And now I have this equation. I'm going to leave it here, and let's start with right chart. Because we're not adding any new solution or any new substance into it, we can just add this HCO3 minus to water and find the concentration of our OH minus to find our pH. So it said we're given with 0.20 molar. Cross this out, everything else is 0 plus x, it'll be x, it'll be minus x, it'll be 0.2 minus x. Now we already found the Kb, so let's just use that. Kb is equal to 2.33 times 10 to the negative 8th, which is equal to x squared divided by 0.2 minus x. We can delete this minus x because of how small Kb is. Now we can do 2.33 e to the negative 8th power times 0.2, take the square root of that, which will give us an x of 6.83 times 10 to the negative 5th. Now we can take 14 plus the log of x, because our x is the concentration of OH minus. So that's why we need to add 14 to it to give us our pH. Okay, now 14 plus the log of the previous answer will give us a pH of 9.83. And that is our pH. And that is it for this series of Buffer's practice problems. Thank you for watching.